On the first day of 1801, an Italian astronomer named Giuseppe Piazzi noticed a faint object moving against the fixed stars. He tracked it for about 6 weeks. Then it slipped behind the sun and was gone, leaving roughly 40 imprecise measurements and an object somewhere on an orbit nobody knew. A 24-year-old German mathematician named Carl Friedrich Gauss took those measurements and worked out where the thing would come back. In December, astronomers pointed their telescopes where he told them to point and found it. We call it Ceres. The method Gauss used was published a few years later by Adrien Marie Legendre in 1805 under the name least squares. It answers one question. Given a scatter of imperfect measurements, what's the line that fits them best? That question is the whole foundation, so it's worth being concrete about it. Put dots on a graph, house sizes against house prices, say. Draw the straight line that comes closest to all of them. The line has 2 adjustable numbers, its steepness and its height, and least squares tells you how to set those 2 numbers so the total error is as small as possible. Once you have the line, you can hand it a house size it has never seen, and it will give you a price. That's regression. It's in every spreadsheet program under the name trendline. It's 220 years old, and it is, unchanged, the thing underneath every system currently being described as artificial intelligence. 2 things had to happen to get from that line to a chatbot, and neither of them is new mathematics. The first is that straight lines aren't enough. Almost nothing real is straight. Price against size flattens out at the top of the market. Dose against effect rises and then plateaus. A straight line through a curved reality is wrong at both ends and right only in the middle. So you let the line bend. In 1943, a neurophysiologist named Warren McCulloch and a logician named Walter Pitts published a description of a nerve cell as arithmetic. Signals come in, each counts for a certain amount, they're summed, and past a threshold the cell fires. That threshold is a bend. Below the line, nothing. Above it, output. Modern systems use gentler bends with names like sigmoid and rectified linear unit, but the job is identical. Somewhere in the calculation there's a kink, a place where the response stops being proportional. The second thing is stacking. Take the output of one regression and feed it into another, and that one into another after that. And here the bend turns out to be load-bearing in a way that isn't obvious. Take a flat sheet of paper and stretch it however you like. Stretch it 1,000 times, in 1,000 directions. It stays flat. Straight lines composed with straight lines produce a straight line, always. And 100 stacked layers of pure regression collapse mathematically into a single regression. You'd have gained nothing but electricity costs. Put one fold in the paper and stretch it again, then fold, then stretch, and within a few rounds, you can make almost any shape you want. That's the entire architecture. Regression stacked in layers, with a bend between the layers. There is a theorem from 1989, proved separately by George Sabenko and Kurt Hornick, saying that a network built this way can approximate essentially any continuous relationship you like, given enough width. Any curve, any surface, any function. The vocabulary changed on the way to the present, which obscures how little else did. The adjustable numbers in Gauss's line are called parameters now, or weights. A stack of regressions is called a deep network, and deep just means there are a lot of them. Training is still least squares, or a close relative, still hunting for the setting of the numbers that makes total error smallest. So, the idea was available in 1943, and the framing was available in 1805, which raises your question. If the mathematics was sitting there, Why did none of this work until roughly 15 years ago? Three things were missing, and they went missing in different ways. The first was a method for tuning the middle. With Gauss's single line, you have two numbers and a clean formula for both. Stack 5 layers, and the numbers in the middle have no direct relationship to the answer. They influence the layer after them, which influences the next. And when the final output is wrong, you have no way to know how much of that error belongs to any particular number buried in the middle. Think of a dish coming back to a kitchen wrong. 3 stations touched it: the prep, the grill, the sauce. With 1 cook, you know exactly who to talk to. With 3, and no way to taste the dish between stations, you are guessing. Frank Rosenblatt ran into this directly. In 1958, he built a machine at the Cornell Aeronautical Laboratory called the Mark I Perceptron, which had 400 light sensors for an eye and stored its adjustable numbers as physical knobs. Potentiometers turned by small electric motors when the machine got something wrong. It was a single layer, and it worked, and it could only draw the equivalent of 1 straight fold. In 1969, Marvin Minsky and Seymour Papert published a proof of exactly what that limitation ruled out. Everyone understood that more layers would fix it. Nobody could train more layers. The fix, and this is the part of the history that refuses to be tidy, because it isn't one discovery at one moment, but the same idea surfacing 3 times in 16 years among people who mostly didn't know about each other, went like this. In 1970, a Finnish master's student named Seppo Linnainmaa published an efficient way of tracing a final result backward through a long chain of nested calculations to see how much each step contributed. And he wasn't thinking about neural networks when he did it. In 1974, Paul Werbos worked out that this same technique could train layered networks and wrote it into his Harvard doctoral thesis, where it sat unread by the people who needed it. And it took until 1986, when David Rumelhart, Geoffrey Hinton, and Ronald Williams published in Nature, for the field to actually adopt it. We call it backpropagation. It's the method for walking backward through the kitchen and apportioning blame. The second missing thing was examples. Regression learns from data, and the number of examples you need scales with the number of adjustable numbers you're trying to set. Gauss set 2 numbers using 40 observations. A modest network from the 1990s had tens of thousands of numbers and needed tens of thousands of labeled images. A useful vision system needs millions, and somebody has to look at each image and write down what's in it. That work simply hadn't been done. In 2009, Fei Li and her collaborators finished ImageNet, millions of photographs labeled by people, one at a time, through crowdsourced work. The third was arithmetic. Training means adjusting every number a little, checking the error, and doing it again, millions of times over. On the machines of the 1980s, a serious training run would have taken months and might have produced nothing usable at the end. What broke that open was an accident of hardware. Graphics cards were built to draw video game scenery, which requires multiplying enormous grids of numbers very fast in parallel. Neural network training also requires multiplying enormous grids of numbers very fast in parallel. The 2 jobs turned out to be the same job wearing different clothes, and nobody planned that. In 2012, Alex Krzyzewski, Ilya Sutskever, and Geoffrey Hinton entered the ImageNet competition with a layered network of about 60 million adjustable numbers, trained on 2 consumer graphics cards over roughly a week. It won by a margin that made people check the scoring. Its design was close kin to what Yann LeCun had built in the late 1980s, back when he was using layered networks to read handwritten digits on bank checks. The architecture wasn't the advance. The advance was that it finished. 5 years later, a team at Google published the transformer, which added a way for the calculation to weigh which earlier words matter for the word currently being processed. You do this constantly. In the sentence, the trophy wouldn't fit in the suitcase because it was too big. You know what it points at. And you know because you weighed the earlier words. That weighing is, again, a set of adjustable numbers set by regression. And the training examples were already sitting there because people had spent 30 years filling the internet with text. So, the mathematics from 1805, the bend from 1943, the training method from 1974, the label data from 2009, and the hardware from a video game industry that wasn't trying to help. The last two arrived within 3 years of each other, and that's the whole reason the timing looks sudden from outside. Gauss did his with a pen on about 40 observations in the winter of 1801.